I heard you just woke up. Your friends were saying that. All right. Anyhow, very good morning to all of you. I hope everybody is fine. We have reached towards the end of our course. Thankfully, we covered most of the things within our online lectures. And this is the first layer from top, or the last layer, that is the layer 7 from bottom up approach. And this layer is known as the application layer. Within two classes, hopefully we should be done with the application layer as well. Uh, these are the things that we'll be studying within this application layer. We'll get to know what application layer is, what it's supposed to do, what are the protocols that are within the application layer. We'll study all of these. If you see the sheet that I have provided you at the beginning of OSI, within that the number layer is 7, name is application. There are OSI protocols given, there are TCP IP protocols also given. Like OSI protocol is RTSC, ACSC, ROS, DAP, and so on. Most common protocols that we know among the application layer are from TCP IP, that is the SIT, that is the Session Initiation Protocol, DNS, FTP, Gopher, HTTP, NFS, NNTP, NTP, that is Network Time Protocol, DSCP, SMPP, SMTP, SNMP, Telnet, RIP, and BGP. So quite a number of protocols are there which basically are within the application layer. And also, we know that this is the layer which is available in end-to-end systems. That's why the protocols that we have are end-to-end protocols. The application layer is present only in the sender and the receiver. No intermediate nodes such as routers, hubs, switches, and so on are oblivious to these things. So what basically is application layer here? Application when a process runs within our operating system, it produces some data which we might need to transfer between different systems. Wherein if we need to transmit the data from one system to another system, we would require data to be sent across the network outside your PC, outside your domain. We would require RPC there, that is remote procedural calls. This we studied very well in operating systems as well, wherein we had the concepts of sockets and APIs. So basically that process would generate some data, and this data is taken by the application layer and then forwarded through the protocol stack, then to the communication link and to the destination. And in the destination side, this would be taken up through the protocol stack, taken by the application layer and passed on to the receiving process. So these are some of the examples. Before, here we can see what I was explaining. We have programs running on end systems. For example, in this case, we have mobile here, and it connects to the server here. Now, they are on two different systems, so we need to send the data across the certain softwares to do that. So here you can see how application layers communicate with each other. In this case, we have a client-server architecture, a client requesting this server for certain things. Now, network in between, like routers and other devices, do not have this application layer protocol. So application layers only run in the end system, which I just explained. So applications in other sense provides us a way to create messages. Application layer establishes an interface to the network as well. And also application layer will provide us some rules and format that govern how the data is to be treated. And a single executable program can use all these three components. For example, if we have Telnet, we took the example Telnet previously as well. Telnet is an application which creates the message. Telnet has a service which establishes an interface to the network, and Telnet is a protocol which provides the rules and formats that govern how data is to be treated. So the first architecture that we see here, client-server paradigm. This client-server architecture is an application layer architecture that we see here. In this, we have a server given on this end, and we have a client which is here as well as here. Server is always on. It has a daemon which is always listening to the incoming web requests. And then we have a client which would communicate to the server whenever it requires it. It may not be necessarily continuously connected to the server. Now, in this case, certain examples of protocols that may be used by this type of architecture are HTTP, IMAP, FTP, and so on, like web browsing, email, downloading a file. The second architecture that we have for applications, we are discussing this time application architectures. The first one being client server, the second being P2P, peer-to-peer. Now, you might ask a question here that we discussed P2P in physical layer. We discussed it this while we're discussing the topologies as well. Now, how is it different here? The difference here is the way you put these, the layout of the nodes with respect to, let's say, this one, client server. How do you lay the cables? How do you lay the wires, the routers, and so on? Physically creating a client server architecture comes there. But with respect to the software, with respect to the application, how do you connect these? We take it in the application layer. So that's basically the difference here. And the second one that we have is peer-to-peer. So peer-to-peer architecture here, P2P, we do not always need a server here. It can be between any end systems who communicate directly between each other. Okay. We have P2P file sharing generally that we do. They can be intermittently connected. Examples are given here in the picture. There is, it's not mentioned here, but there is another one which is hybrid of client and peer-to-peer. I'll mention it here. As the name itself depicts, that it would be a mixture of the two, in which we'll have a client server as well as P2P within it. So what we see here in application layer are basically processes communicating with each other. We have a program running in the host, program running in the server. Host as in client initiates the communication. Server is waiting for web requests. So basically server has a process that waits to be contacted. Here is the difference which we have already discussed in OS. One is the inter-process communication and another is the remote procedural calls. Since we are talking about processes communicating, and if processes are communicating in different systems, we are talking about remote procedural calls. Okay. Here a question, let me go back here. I mentioned here after peer-to-peer, I mentioned hybrid of client server and P2P. The example of client server is here. The example of peer-to-peer is here. But I was expecting, let's say, a question of hybrid. I'll write here again. Hybrid of client server and P2P. So what is the example of hybrid of client server and P2P? Skype. It's common video conferencing application is a good example of the hybrid. How? We have VoIP P2P application, that is Skype. It has a centralized server. How? How do you connect to the other person? You don't directly connect the other person through Skype. You would need a user ID, email ID, or some sort of ID which would help you in connecting to the other party. So who helps in this? Centralized server helps in this. So centralized server helps in finding address of a remote part. Are connected, and once you are communicating, you now have a video and audio, you have a connection created, you have a client to client communication or connection, and this one is direct, not through the server. So the first part, that is centralized server, it would look like this one. This one. That this is your phone and this is the Skype server, and then this is the laptop also connecting to the server. You get connected. The next you have phone connected to the laptop directly. And the hybrid here helped you in having both of these, first centralized and then first client server and then peer-to-peer. This is the best example that we can have. That's instant messaging and so on. I hope this is clear, the hybrid one. Okay. Now moving on to the sockets. Now we know that process sends as well as receives messages to and from its socket. So when a program is running, it has to send the data across. It would utilize the services of socket. If you remember the example that I have given of socket, socket is typically a door to it. So the sending process sends out the message through the door. Then it would pass on to the underlying process. It's like process gives it through the application layer to the lower layers as is shown in the figure here. In the receiving socket, the socket receives the data and then pushes this data onto the application, that is the receiving application. So if you remember, you had a Facebook Messenger as well as you were running a website, you're opening a website, let's say in Chrome. And now you are using both the applications to communicate over the internet. When the data is sent and received back from the internet, it has to ensure that this data goes to the appropriate application. So that's why we say that a process should have an identifier to receive the message. And how do we make this identifier? We use socket as an identifier. And what is a socket? A socket is a combination of two things. One is the IP address plus the second is port number. This we have previously discussed, if you remember. So identifier, I got a packet, let's say 2 packets now at the receiving end. Now, let's say I'm chatting. Now I said hi, I got hello back. This hello is to be sent to Facebook Messenger, and I went to a website through Google and this data is also received. I have 2 different packets. One packet is destined to Facebook Messenger, another packet is destined to the Chrome. Now how would I differentiate which packet goes to which? I would require an identifier, and the identifier that I have here is the socket, and the socket is this IP address plus port number. So if I have an address here, this port number 80, typically used for HTTP, this means that this is my socket. Is this clear? Any questions? Okay, then we move on to the application layer protocol, what it actually does. It defines the types of messages that are exchanged, whether it's a request or a response. An example would be HTTP request and HTTP response. What would be the syntax within that request and response fields? What would be the semantics, that is the meaning of the information within these? And also, the application layer protocol would define the rules of when and how to process with send and response messages. There are 2 different varieties of protocols that come in an application layer. One is open protocols like HTTP, SMTP. It allows interoperability. It's in the sense that you create an application, you define HTTP as a protocol. There's no issue with this. The another one is proprietary protocol like Skype. Within this, they belong to an organization, let's say Microsoft, and these protocols cannot be copied. What transport service does an application need? We come to certain services which an application would require, like the data loss, the throughput, timing, security, and so on. And then we can have a good comparison of like what application needs what. The first one is data integrity, timing, throughput, and security. Data integrity here we can define with terms of data loss. Some applications can tolerate loss, some cannot tolerate loss. The example of application that tolerates loss is audio video. You're watching a cricket match, you want it timely, we have discussed it. You will say, okay, some frames may be lost, but I want the delivery of some frames on time. So you can tolerate some frames that can be lost. Some applications are there which would require that not a single bit be corrupted. In that case, we want 100% reliable data. For example, you are downloading an email, you're downloading a file, and so on. In this case, you cannot afford any loss. Some need a good throughput, that is the second one, like multimedia contents. So we have like elastic applications and inelastic application. Elastic application would be like whatever throughput you have, we'll use it and we'll try to see it. Like you are checking your email, may take time to download an attachment or open your email, fine. But some require a minimum amount of throughput but wants to be effective like multimedia applications. Number 3 is the timing. Typically games that you presently play like PUBG, you would want the ping of that game to be minimum. So interactive games or VoIP telephony and so on require very less delays. Some applications would require a good amount of security. So here is the comparison of common applications that we have. Applications like file transfer or download, you cannot bear any loss. Throughput is elastic, sometimes it may be more, sometimes it's less, no issues, and it is not sensitive to time. Same is the case with email, same is the case with web documents. Okay. Same may be the case of text messaging, but however, in case of text messaging, you would want that time sensitivity may be there if you are instantly messaging and you want an instant message back. As compared to this, you compare these 4 things with real-time audio, video, streaming audio, video, interactive games. They are loss tolerant. They can bear some loss. Throughput is mentioned here. They would want this kind of throughput. And time sensitivity is there. They are very sensitive to time, these kind of applications. This is the transport layer protocols that we have. We have done this TCP as well as UDP services. We have done a comparison of both of the two. Why we are taking it? Because our next slide here tells us that if we have an application, what transport layer protocol do we use? And what application layer protocol do we use? Now, if you're using, try to get this, I mean, this is an important slide. If you're using an application which is file transfer, you're downloading a file, the application protocol that it uses is FTP, that is file transfer protocol, which is RFC mentioned here 959. And the transport layer protocol it has is TCP. Remember three-way handshake and all. Then we have email. The application layer protocol that is SMTP, which is simple mail transfer protocol. Simple mail transfer protocol, RFC 5321. And underlying transport layer protocol is TCP. Web documents, HTTP, hypertext transfer protocol, underlying TCP. Then internet telephony, SIP, that is session initiation protocol, RTP, real-time transfer protocol, or real-time protocol, or any proprietary protocol like we use for Skype. We can use either TCP or UDP. Likewise, for streaming audio, video, it's mentioned here, interactive games, and so on. So this is a good slide explaining the protocols of application layer and then the protocols of transport layer. The next thing is securing TCP. Do you have any questions till now? Okay. We have after this web and HTTP. We understand HTTP is hypertext transfer protocol. Okay. That's mentioned here. And why we are taking HTTP? Because obviously it's an application layer protocol, and a best example that we'll have for HTTP for an application protocol, because it uses TCP, it is stateless, and a good example of response and request response is within this HTTP. A quick review: web page consists of objects, each of which can be stored on different web servers. This we have discussed also while we are doing threading. Like we have an HTML file, we have JPEG image, we have Java applet audio file, and so on. This example we took when we did not want a complete, blockage of a process. If we had multi-threaded objects, then some threads would run and some can stop, and some would be faster as well. So if text got downloaded before, we can read the text until the video, flash, audio, or some other picture, some other object would get downloaded. Now we are seeing this from the network aspect. So base file that we have is an HTML file. Now it includes certain other reference objects such as the picture. So this is the host name, this is the path where it has been kept. You can have different folders within the same server or a different server. This is the overview of HTTP, that's hypertext transfer protocol. Web's application layer protocol. It uses a client server model. Client browses, let's say a client has Chrome as a browser, and it sends a request which the server receives here. As mentioned earlier, the server, let's say it has an Apache web server. Web server's purpose would be to continuously keep a daemon running, and the purpose would be to listen to the server requests. And now once the request is sent, the reply from the server would be HTTP response request. Sorry, request is HTTP from the client to the server, and the server replies back with an HTTP response. Both use HTTP protocol. And likewise, there would be some other device as well who would be sending a request and getting a response. This is what we have as a client-server model. HTTP has a base protocol of transport layer, which is TCP. It creates or initiates a TCP connection, creates a socket to server using port 80. Port numbers we discussed in the transport layer. And while we are discussing port numbers, we discussed that from 0 to 1023 port numbers, these have been kept as reserved port numbers. Why reserved? They are known as well-known port numbers. They are reserved for well-known protocols, and one of the well-known protocol here is HTTP. Then we had FTP, Telnet for remote login, and so on. So this is the socket to server connected through port 80. Server accepts the TCP connection from client. Then application layer protocol messages are exchanged between client and the server. Whatever you have to send, you will get it. Upload, download happens. And at the end of the connection, you need to terminate it because it's a TCP connection, three-way handshake. The TCP connection is closed. Another thing that we have here is that HTTP is stateless. What we mean by stateless here, it means that the server maintains no information about past client requests. Some protocols that maintain state are complex in the sense that they keep a history of the past clients. The next thing is the types of HTTP, and HTTP comes in two flavors. One is known as persistent HTTP and another is known as non-persistent HTTP. Here is a comparison of non-persistent and persistent HTTP. The main difference between persistent and non-persistent is that in persistent HTTP, we can have multiple objects sent over a single TCP connection. I would mention it. I would highlight it here. Multiple objects can be sent over a single TCP connection between server and client. Whereas in non-persistent, we have at most one object sent over TCP connection. What does that mean? That means that if we have non-persistent HTTP, we would require multiple connections to download multiple objects. But in case of persistent HTTP, we can have a single connection downloading multiple objects. So obviously persistent is good. This is an example of non-persistent. So HTTP client here initiates TCP connection to HTTP server. We can see here. Now the server side replies to the TCP request saying that I accept the connection. Then the host sends a request message indicating what exactly it wants. The server replies back containing the object that has been requested. After the data has been sent, HTTP server closes the TCP connection. That's the first one. Now, the client side, after receiving the response, checks the HTML file and finds that within this file there are several other objects which have been referenced, like an image, a flash file, a video, an audio file, and so on. Now what it does? It does steps 1 to 5 once again. That is number 1A that is given here. Now it will send a request for image. First send a connection, accept the connection request for the image, then gets back the image. Then for the second thing, third thing, then so on. And it would do it again and again. And this connection would be for each object that has been referenced within that HTML file. Separate connections, separately downloaded each object. So what do we have here in non-persistent HTTP response time? We have twice the round trip time, RTT time, which is the time for a packet to travel from client to server and back. That is given here, plus file transmission time. Here you can see there is one RTT to initiate the TCP connection, one RTT for HTTP request, and then the file transfer. Compare this with persistent HTTP, that's 1.1, HTTP 1.1. Non-persistent requires 2 RTTs per object, while as in persistent HTTP, server leaves connection open. It does not close it after sending the response. There is an operating system overhead for each TCP connection, whereas in persistent HTTP, subsequent HTTP messages between the same client and server are sent over the same open connection. You do not have to create this connection again and again. You simply use the created connection for all the other messages that has been transferred between the server and the client. Okay, so in persistent HTTP, if we compare the RTTs, we will have one RTT for all the referenced object, thus cutting the response time into half. Whereas in non-persistent, it requires 2 RTTs per object. The next slide that we have explains how an HTTP request looks like. So when as a client you send a request to web, let's say you go to google.com, okay, what do you actually send to google.com? Till now we have been mentioning you are requesting, but what basically is this request? So HTTP has 2 types of messages. One is the request message and another is the response message. Here is how ASCII type or human readable format of HTTP looks like. So this is what you are actually sending. That is within this pink box. The first part says get. So this is a request. This page using the protocol HTTP. This is 1.1, the version of HTTP are carriage data character and line feed character. Then you are, this is the page that you are getting. This is written, this is the protocol. This is written in this HTML language and this is the name of that page. Then where from do you get this index.html? You get it from the host, which is this one. Who is sending this request? It's a Firefox browser with this version whose send a request. Accepts text HTML application type XHTML plus XML. The language should be English United States. It accepts the encoding of zip and deflate. Character set should be this, keep alive for this much, and connection is keep alive. This is what you have requested. You have given a lot of things that you accept, a lot of information that you are sending. In fact, you have told them what browser you are sending it across through and what protocols you are expecting, what things you are expecting from your end. This is the format of it. This is how it looks like, the HTTP request. Any questions, Silo? And likewise, we would have a response message as well. This is HTTP response message. The first thing that we have within it, mentioning the protocol. Now, let's say you made a request to a server and server is replying back saying I'm using HTTP 1.1. This is the status code, the date on which is sent, the server. Now, since you requested, you said I'm using Firefox, the server says I'm using an Apache server, web server, which is having this version, and CentOS OS, this is the operating system I am running on. This is the last modified, the page, and other details like what it accepts, the range, what is the length of it, the connection time, when it timeouts, keep alive connection, what is the content, it's a text and HTML, what character set you are using. And after this is basically the header lines that you have while sending back the response message. Then you would have the actual data after it, the data that you had requested. So these are the things, these are the, just now I mentioned here, HTTP 1.1, then it's written 200, then okay. What is this 200? I just said status code, status phrases. What type of status codes we have? There are sample status codes given here. 200 okay means request succeeded, requested object later in the message. 301 permanently. The requested object is moved, new location specified later in this message. So you will be redirected. There will be a message that this page has been moved. Now you can please go to this link to get that object. 400, bad request. Request message not understood by server. Okay. Maybe you have mentioned certain things which server could not understand within it. 404, page not found. Okay, the requested document is not on the server. 505, HTTP version not supported. Like for example, here we have HTTP 1.1 and the sender request also was HTTP 1.1. Because of some differences between HTTP request, we can have a difference here which would say HTTP version is not supported. So this is basically what we have as HTTP request response. There are other HTTP request messages as well, like we have post message and get message, head method and put method that we call it. Here is an example of trying out HTTP for yourself, client side. Telnet, we have done Telnet in our lab work. So this is the idea of the same thing. If you want to see again, you can Telnet and see how it works. Okay, I'll stop here. I would want you to go ahead and have a look again at Telnet, like the example has been given here, so that you get an idea of the HTTP request response in the Telnet. Do we have any questions? Any questions? No? All right, Ramanand, we'll stop here. We'll continue with it tomorrow. What about the first quiz missed by some students? Yes, I'm thinking about what to do with that. It